Hi everyone, welcome to the sixth video of searching and sorting. Today I'm going to write a program to count number of perfect squares that are less than a natural number n. Let's consider this example where we have an array of n elements and n is equal to 9. The square root of 9 is 3, which means it's a perfect square. Since we have an array of natural numbers up to 9 and the array contains the square of 3, it means the array would also have the squares of all the numbers which are less than 3, which is 1 and 2. So we have 3 perfect squares up to number 9, which are 1, 2 and 3. But we need the perfect squares that are less than n or 9 in this case. So the answer would be 2. Now let's write the logic for this problem. The first case is when n is a perfect square. Consider n is equal to 9. The square root of 9 is 3, so we can write it as 3 into 3 is equal to 9, or m into m is equal to n. So the answer would be m minus 1 or 3 minus 1, which is 2. We have subtracted 1 because we have to look for the squares that are less than n. Now let's consider n is equal to 10. In this case, the n is not a perfect square as its square is 3.16, which means we don't have to ignore n by subtracting 1. So the answer would be m. So there are two conditions that we need to use to solve this problem. And here is a program that I have written. The first thing is I'm taking the floor value of square root of n. You could ignore this as we are already using int, which will ignore any decimal. Next, I'm checking if r into r is equal to n. I'm returning r minus 1, else I'm returning r. So this was a very simple problem, but if we are asked to solve this problem without using any built-in function like square root, we have to make use of a binary search. But before we start talking about binary search, I want to mention one thing, which is the square root of n is always less than equal to n by 2. Consider n is equal to 4. The square root of 4 is 2, which is equal to n by 2. Consider n is equal to 9. The square root of 9 is 3, which is less than 4.5. Now applying the binary search in this given array, where n is equal to 9, L would be 0 and H would be n by 2, which is 4. And the value of m would be 0 plus 4 by 2, which is 2. Now I will iterate through the array while L is less than equal to H. And the first condition that I'm going to check is if the square of m is equal to n. In that case, I'll return m or the index. Here m is 3. So 3 into 3 is 9, so I have returned 3. But we have to ignore n, so we will return 3 minus 1, which is 2. So the next condition is if m square is greater than n. In that case, the square root is less than the middle value. So we will change high to mid minus 1 to traverse the left half of the current search space. And the last case is when m square is less than n, which means the square root of n could be greater than m. So we will traverse to right half of the current search space by changing low to mid plus 1, or in this case L would be equal to m plus 1. To understand this last case, consider n is equal to 15. The L is 0, H would be n by 2, which is 7. The mid is 7 by 2, which is 3. Here m square is greater than n, so we'll change h to m minus 1. The value of h is now 3 minus 1, which is 2. And the mid becomes 2 by 2, which is 1. Now 2 square is less than 15, so L becomes m plus 1, which is 2. So the values h, L, m all would be equal to 2. And at this point the loop will terminate and we will not get any answer, whereas its answer should have been 3. So in case when m square is less than n, the m could be a possible square root or the answer. So we will store this value of m in a variable named answer, and we will return this answer in case the loop does not return any count or number. Now let's write the code in the IDE. So inside this function, I will check if n is equal to 1. In that case, I'll return 0 because there won't be any perfect square that is less than 1. Next, I'll set the value of low to 0 and high to n by 2. Next, I'll use a while loop which will run as long as the value of low is less than equal to high. Next, I'm defining the mid, which is low plus high by 2. Next, I'm checking if mid square is equal to n. In that case, we'll return mid minus 1. Else I will check if mid square is greater than n. In that case, the high would be mid minus 1. Else the value of low would be mid plus 1. So in this case, the mid could be a possible answer. So we are storing this value in a variable called r, and we will return this r outside the while loop. Now let's compile and run the program. And this test case has been passed, so if I submit this code, it should work fine. And here our code has been accepted. The time complexity of this program would be big O of square root of n by 2, because we divided the search space to half even before applying binary search. I hope you understood the program. Thank you so much for watching. I would keep making such videos. I just need your support to help me stay motivated. Thank you so much for watching. Have a great day.